Okay, we'll start with section 5.4, which is the last section of this chapter, and this is also on annuities, but we'll study the present value problem and the amortization problem. So in the previous section, we learned about annuities where we deposited funds regularly, and this was the accumulation or the increasing stage of the annuity. So the balance in the annuity was increasing and we computed its future value. So annuity increased from 0 at the beginning to some larger value at the end. So in the previous section, we started with $0. We deposited funds, and after T years, we wanted to know what was future value. Now we will study the present value of an annuity that it must begin with so that this annuity can provide regular and equal payments. That is, one can withdraw funds regularly over the term of the annuity till its balance is 0. So this is the withdrawal or the decreasing stage of the annuity. So this is what we are interested in now. In other words, here is your time 0, and now we are withdrawing money from it. So we are going to withdraw PMT amount for T years till the balance becomes $0. So the question is, how much should it have in the beginning so that you can withdraw this amount every month or every quarter or every year, whatever it is, for T years. Now it is earning interest while this is happening. So that's why it is an annuity, but it's decreasing annuity. So we would like to know the present value of an annuity whose funds are compounded monthly at an annual interest rate of 3%, which can make a regular payment of $1,000 each month for 10 years. So let's look at the diagram for this. So this is times 0 and this is 10 years. So for 10 years we want to withdraw $1,000 from it every month. So this is each month we are going to withdraw, so each month. And it's paying 3% annual interest rate. So the question is, what should be the present value? That means how much should be the balance in this annuity now so that one can get $1,000 every month for 10 years. So we're going to do this problem in a minute after we see the formula for it. So few notes. The annuity is an ordinary annuity since the payments are made at the end of each period. So at the end of the month is when you get your $1,000. As before, the frequency of payments is same as the frequency of compounding. So if the payments are monthly, the compounding is monthly. At the end of the term of the annuity, the balance is 0, and that's why it's called a decreasing annuity. The present value of the annuity is PV, and the regularly scheduled payment is PMT. The rest of the terms are same as before. That means the I and the N that we have been finding stays the same. So the formula for this problem comes out to be this. So that means the present value is PMT times 1 minus 1 plus I raised to the power negative n. So please notice negative divided by I. So it's very similar to the previous one, but obviously it is different and you have to be very careful. So the formula is similar that we have seen, but the exponent is negative n. So you have to be very, very careful when using your calculator. So let's continue finding the present value for this situation. So we know the payment is $1,000. R is 3%. M is 12 because we are withdrawing every month, and time is 10 years. So from here our I is 0.03 over 12, which is 0.0025, and N is 12 times 10, which is 120. So we now go and substitute these numbers in this formula, and we get PV equals 1000 times 1 minus 1 plus 0.0025 raised to the power negative 120. The whole thing divided by 0.0025. Again repeating, you have to know exactly how to enter a negative exponent in your calculator, and you should practice this quite a bit. And if you do this, you're going to get 103,561 and 80 cents. So if we have $103,561.80, then this annuity will be able to provide $1,000 withdrawal each month for 10 years. So let's practice this kind of problem a few more times. So the question is, find the amount necessary to fund the given withdrawals. So we want to make quarterly withdrawals of $730 for 5 years, and the interest rate is 4.5%. So clearly PMT is 730, R is 0.045, M is 4 because it's quarterly, and we are withdrawing for 5 years. So from here we can find I, and that'll come out to be 0.01125, and N is 4 times 5, so that's 20. So the question is, what is the present value? That means what is the amount necessary to fund these withdrawals? So how much should you have in this annuity now? Okay, so we know the formula. So let's go and substitute. We get 730 times 1 minus 1 plus 0.01125 raised to the power negative 20 over 0.01125. So as before, one should find this number first, and if you do that, you will get 17.82045, and then you would multiply by 730, and when you do that you're going to get 13008.93. So that means if your annuity has $13,008.93, then you can withdraw $730 each quarter for 5 years. Another example. Find the payments made by an ordinary annuity with the given present value. So that means the present value is $680,000. It's going to make quarterly payments for 10 years and the interest rate is 5.6%. The question is, find the payments that it can make. So this time I know the present value, and rest of the things are pretty standard by now. M is 4 and time is 10 years. So again, I is 0.014, N is obviously 40, and we have to find the payments that it can make. So let's write down the formula. This you would have on your formula sheet. Now let's substitute. So I know PV this time, so that is 680,000. PMT is what we don't know, and the rest of the guys are 1 minus 1 plus 0.014 raised to the power negative 40 over 0.014. And again, you should do this arithmetic using your calculator, and you're going to get 30.46915. 30.4646915, and therefore PMT would be 680,000 divided by this number, and that will give you 22317.65. That means every quarter this annuity is going to pay you $22,317.65. Next example. How much should Anne Marie have in her annuity so that she can withdraw $1,000 every month for the next 10 years if the annuity is paying 3% compounded monthly? So this is a typical retirement planning question. So Anne Marie knows that she's going to need $1,000 every month for the next 10 years, and she would like to know how much she should have in her annuity. So PMT is 1,000 because that's the payments coming out of the annuity. R is 0.03. She wants it monthly, so M is 12, and it is for 10 years. So 0.03 I is divided by 12, and that would be 0.0025. N is 10 times 12, so that's 120. So therefore the question is to find the present value. So substituting in our formula, we get PV is equal to 1000 times 1 minus 1 plus 0.0025 raised to the power negative 120 divided by 0.0025. And again, the usual routine, use 1000 times, and when you do the arithmetic for the rest of it, you're gonna get 103.56175. So multiplying is easy. It's 103,561.75. So that means Anne Marie's annuity should have $103,561 approximately. So this is the amount. This is pretty close to this, so it's just because of rounding. Sometimes it could come out to be like 80 cents. Here it's 75 cents. The final application for this kind of question on present value is of amortization. Now this is a very important application. Certain kinds of loans, such as auto loans, home mortgages, are paid off by making regular payments of equal amount to the bank. So for example, if you have an auto loan, you could be making a payment of $250 every month for 5 years. So it's the same amount for a fixed number of years and regularly made every month. This process of paying off a loan is called amortization. From the bank's point of view, the borrower's payments are an annuity that is paying it a fixed amount at regular intervals till the loan is paid off. So, how is this problem set up? So, in short, for such loans, consider the loan amount to be the annuity's present value. So, whatever is the loan amount is actually equal to the present value of your annuity, and the term of the loan is the term of the annuity. So T is how long is the loan for, and the frequency of payments is the same as the frequency of compounding. So M is obviously the frequency of payments, and what we have to find is what is the payment, monthly or quarterly or yearly. So PMT is what we are normally looking for. So let's look at an example of amortization. So we want to find the payment necessary to amortize the following loan. So the loan amount is $1,400, interest rate is 12%, it's quarterly payments over 2 years. So what should be the quarterly payments? So let's see, PV is supposed to be the loan amount. So present value is $1,400, R is 12%, M is 4 because we are making quarterly payments, and the length or the term of the loan is 2 years. So from here, I is 0.12 divided by 4, and that is 0.03. N is 4 times 2, so that's 8. So substituting in our formula, we get 1400 is equal to PMT times 1 minus 1 plus 0.03 raised to the power negative 8 over 0.03. So again, using your calculator, you can find that this is PMT times 7.01969. So therefore PMT, the payment would be 1400 divided by this number, and when you do that, you get $199.44. So the idea is that if somebody makes a payment of $199.44 every quarter for 2 years, then this loan of $1,400 will be paid off. It's a very important kind of problem to solve. And here is our final example. This is a classical mortgage question. So find the monthly house payments to amortize the following loan. So this family has borrowed $400,000 at 6% for 15-year mortgage. What is the monthly payment? And then after that, we have to find out how much interest did they pay on this mortgage. So let's first do this. So our present value is the loan amount, so which is 400,000. Interest rate is 0.06. M is 12 because they're making monthly payments. And T is 15 years. So this is a special kind of mortgage, 15-year mortgage. Normally mortgages are 30 years. So you could obviously practice doing a problem where the time is 30 years. So from here, my I is going to be 0.005 and N will be 12 times 30, which is 360. No, it's 12 times 15 because it's a 15-year mortgage. So that will be 180. Okay, so we are ready to substitute. 400,000 is PMT times 1 minus 1 plus. Again, reminding you, this is a negative exponent, negative 180 divided by 0.005. And again, use your calculator carefully and find this number, which will be 118.5035. Therefore, the payment would be 400,000 divided by 118.5035, and that should come out to 3375.43. The answer may be slightly off from this number because I'm only keeping 4 decimals here. So monthly payment would be $3,375 and 43 cents. So this family would be paying monthly this amount for 15 years to pay off a $400,000 house. So then comes the question, what is the interest paid? Well, how much money did they pay over the years? So total payment is 3375.43 multiplied by 180 payments. Remember, there are 180 months in 15 years, so they wrote 180 checks. And therefore, the interest they ended up paying is this amount minus 400,000 because that was what they had borrowed. So you multiply this and subtract 400,000 and you're going to get 207,577.40. So in 15 years, they ended up paying $207,577 in interest. A pretty shocking amount. So a house that they bought for $400,000, they ended up paying more than half the price of the house as just the interest. There are many such interesting questions in mortgages and in other amortization loans. You could practice this question by having a 30-year mortgage. So you could practice same numbers. What you can do is make t equals 30, which is more conventional, and find the interest paid. And that'll be even more shocking. So if you take 30 years to pay off your house, the amount of interest that you're going to pay will be far, far more than this. So this is bad enough, but if you have a 30-year mortgage, it will be even worse.